I'm really pleased to introduce a special colleague and a friend of mine from Ball State in Indiana. Mike Karls does lots and lots of activities with students, and I find it amazing since he's also been serving as the chair of a department. Somehow I think when you become the chair, if I ever became the chair, I couldn't do anything else. But he seems to be able to function that way, as well as have a life, I understand, so that's important. He does a lot of projects with students, and he wants to talk about the notion that projects can drive a course and bring students to real research experiences. So Mike, I'll have you take it away.
Thank you. Can you guys hear me?
Yes, we can.
Okay, thanks.
And it's clear.
Good. Okay, so I want to talk about just the approach I've taken to work with students on undergraduate research experiences. And yeah, so early in my career, I was approached by a Ball State student to be an honors thesis advisor, and I had no idea what it meant to be what does it mean to have an honors thesis project? So I gave the student an open-ended problem to consider, which was modeling heat flow in a thermos. And so not only did the student complete his thesis, but the resulting work led to a refereed journal article and opened the door to a very successful series of collaborative undergraduate research projects. And all the problems have the following in common. They're simple to state, open-ended, student-driven, mathematically significant. They rely on student insight and require a substantial amount of work on both the students and my part. And several of these projects have led to a refereed publication that could be used to illustrate topics taught in the undergraduate curriculum. And so we're going to look at the process I've developed for this type of research, look at what works and what doesn't work, and touch on some of the topics explored. We're going to look at heat flow, cryptography, and diving boards. And so typically what happens is a student contacts me about doing some sort of undergraduate research. And most of these students are in Ball State's Honors College. And part of their honors college requirements is a student does an honors thesis. And other projects have arisen as part of an Indiana space grant. In this case, I contacted some of the students that were involved. So here's some expectations for the project. The students should plan to spend at least a semester or summer on the project. Most projects have taken 2 semesters to complete. And the first semester is spent learning requisite theory, setting up and solving the problem. And the second semester is spent testing the problem solution, implementing it on a computer, and writing up the work. And each thesis has required many revisions before final version meets my approval. And if possible, I'd like the student to present their work. And one venue that's worked well is our departmental undergraduate colloquium. And so for the project, the process involved is each project involves an applied mathematical problem of interest to the student and me. The problems are suggested and tailored to the student's mathematical background. Each requires self-study, learning, and mastery of mathematics that's new to the student. And each involves development of a mathematical problem or model. And each involves solution of the problem or model. And each involves testing the solution with data. And all of them incorporate software and technology, and typically mathematics is what we use. And most have resulted in a refereed publication. Okay, so I'm going to look at 3 sample projects. The first is heat flow in a thermos, and James Serschel is the student I worked with on that. And then I looked at curve cryptography, and Amy O'Malley is the student I worked with on that. And displacement of a diving board, I worked with Brenda Squichellis on that project. Okay, so we're going to look at a problem statement, and then I'll just touch on the mathematical background required to work on this project. Look at some initial attempts and provide some input or insight that came from the students. And then look at the results and how is the project disseminated. Okay, so the first thing is heat flow in a thermos. So the problem here is we want to find a way to describe the temperature of a thermos full of hot coffee at any point in the thermos at any time after the coffee is poured into the thermos. So what sort of mathematical ideas do we need to know? Newton's law of cooling, the idea of an initial value problem, an ordinary differential equation, the idea of a boundary value problem, we should look at partial differential equations. conservation of energy, Fourier's law of heat conduction, the heat equation, and then the idea of separation of variables, and then the idea of Fourier series. And so if you look here, this is the actual model. This is the heat equation, and then we have some boundary conditions here and initial temperature distribution here for our last equation. Okay, so here were the initial attempts at trying to study this model. So my original idea was to use boiling water in a thermos. And then I used temperature probes hooked to CBLs, that's computer-based laboratory. These are little devices that you can hook up to probes to collect data, and then you can dump the data into Texas Instrument calculators. And these are quite old. I think these are TI-85s. And we use these to measure temperature at various heights in the thermos. And besides issues with safety, because we were working with boiling water, there was a question of how to cap off the thermos with temperature probes coming out of the top. And my initial attempts resulted in failure, so no useful data was collected. So then James decided to use ice water instead of boiling water. And this is safer, allows an open top and reduces heat loss due to steam. Unfortunately, the results with this new approach weren't much better than those with hot water. And these are seen in this picture right here. The diamonds are the temperature at the top. And then the squares are the temperature in the middle of the thermos, and the stars are the temperature at the bottom of the thermos. And then the curves are the model, and the open symbols are the measured data. And so then James thought of two other things to change the model. He decided to stick cotton balls into the ice water to make it more like a solid instead of a liquid. And he also assumed that the initial temperature distribution has an exponential term. And this led to the results you see in the second picture here, which are just unbelievably good. I could not believe how good these were. And so this work resulted in a co-authored paper that appeared in the American Journal of Physics. Okay, so there's a picture of the first page of the article. And so the next problem I look at is
just, Mike, can I ask, how
Sure.
long between when your student finished and you got a publication? This is remarkable.
Well, okay, these are a little dated. This came out in it got
2000.
2003.
Okay.
I think he wrote his thesis in 2000. I'm gonna say maybe like 2000. He finished it, or
Okay.
2001. It's got a, yeah, it took about a year to be accepted.
Okay, great. I'm sorry.
It's okay. So this next project is elliptic curve cryptography. And so this isn't differential equations, but it's another applied project.
Yeah.
So find a way to implement a cryptographic scheme known as elliptic curve cryptography by means of software. These are elliptic curves here, these pictures here. And so we had to learn about groups of abelian groups and fields, elliptic curves over the real numbers, elliptic curve groups, elliptic curves over a finite field, elliptic curve cryptography, the discrete log problem, and then the idea of Bell-Gamel method. Okay, so I started with some background material from a paper written by Ezra Brown on elliptic curves. And my initial plan was to implement this elliptic curve cryptography scheme using C. And here's a book I found that talks about doing that. And this turned out to be pretty hard because Amy and I have to learn elliptic curve cryptography. We'd also need to learn much more C than either of us knew. So first of all, we learned about elliptic curves and how to add points on these curves. And so here's a picture. The way it works is you take 2 points and then you draw a line through them and look at where it hits a third point on the curve, and you reflect about the x-axis, and that's the sum. R is the sum of P and Q here. So Amy decided to use Mathematica to work with this. And so she built all these graphs in Mathematica from scratch using help files. And this is some code she implemented in Mathematica to verify an elliptic curve as a corresponding elliptic curve group, construct an elliptic curve group from elliptic curve over a finite field such as integers mod of prime number P, add points on these curves, and implement the Bell-Gamel scheme for an elliptic curve group. Okay, so we actually have a journal at Ball State. It's an undergraduate research journal that students submit stuff. It's actually refereed. So Amy submitted her work to this journal. Oops. And so there's a picture of the first page of her paper. And the last project is a displacement of a diving board. So the problem is to find the vertical displacement of a diving board at any point along the board at any time after the board is displaced and released. And so what do you need to know for this? Well, what is a cantilever beam, Newton's second law, the idea of bending moment, and shearing and damping forces. What is a boundary value problem? The beam equation, which is a PDE. The idea of separation of variables to solve it. Again, Fourier series. So here's the model. This is the beam equation, and then you have some boundary conditions and some initial data, initial conditions here. And so Brenda, her first model was to use the beam equation with a quadratic function for initial displacement. So she just started out with the part of the equation which appears in this little red box here. And we decided that an actual diving board wouldn't be feasible. So Brenda contacted the physics department to see if they had a long ruler we could use. So here's a 2-meter stick we have clamped to a table that we're using, and that's Brenda holding it down. And so, yes, we used a wooden ruler of length 2 meters. And we marked off 15 points with a tape here along the ruler. And we videotaped this and captured data using world and motion software. Now it's called Tracker. And so then Brenda was able to match model and data time period, but decided that damping needed to be accounted for in the model. And so she added in a damping term to her model. And including this term led to much better results. So the dots are the measured data. On one point, I think the end point, open and far right point along the beam, and the curve is the model. And this is as far as we got for Brenda's honors thesis. So we weren't quite where we wanted to be. And so then after Brenda completed her thesis, I continued working on the project. And one day I had the idea to include a forcing term. Turns out that forcing due to gravity is what's needed. And we use I use mathematics manipulate command, and one can implement this model. Well, all 3 models at once. So now what you see is the curve matches the data. And here's a picture of the data measured over time with the model superimposed at each point along the beam. And one of the keys to this approach was Brenda's choice of a quadratic function as the initial displacement function. So this actually got published in Mathematics magazine, a joint paper came out. And so I get wondered this year, where do I get these ideas from? Well, they come from courses I've taught, research projects, or examples in books. So the thermos problem was inspired by a homework question from my boundary value problems class. And the elliptic curve cryptography problem resulted from a sabbatical project which involved cryptography. And the diving board problem was motivated by an example I found in a book on boundary value problems by Nakayama. And I'm always looking for more project topics. So I guess the guidelines for projects are choose a problem that's simple or easy to state and set up regular meetings. Usually I try to meet with students once per week. So if the problem solution is uncertain or unknown, and be prepared to modify the original problem. This happens all the time with stuff I've worked on. And let student input or insight help drive the project. And set high levels of expectation. Students will usually rise to this level. Expect the unexpected. What results from a project is often much better than the initial idea. And the guidelines above, I guess the most important one is to set up regular meetings. That's crucial to a project success. So one of the projects that I worked on, we'll say more recently in the fall, it failed to get off the ground. And mainly I think it's because I wasn't able to meet with a student on a regular basis. So in spring, we did establish weekly meeting time, and that led to a successful completion of the project. So here's some references. So this Napoli Asmar's book is a really nice book, resource for partial differential equations and boundary value problems. And this nice paper by Ezra Brown. It's a real neat introduction to Fermat. He ties in Fermat to elliptic curves. And the world of motion is now called Tracker software. And this is the paper that James and I wrote that appeared in the American Journal of Physics. And this is the paper that Brendan and I wrote that appeared in Mathematics Magazine. And here's the paper that Amy wrote that appeared in Ball State Mathematics Exchange. And then this is the book on implementing elliptic curve cryptography. So I think that's the end of the talk. So thanks.
Well, thank you very much. It's amazing how you've gotten, for your own personal growth, these disparate areas of mathematics. I wanted you to go back and tell us how you get connected to these students. Are they, you know?
A lot of them I've had in class. And so James
Okay.
classes with me. Amy took, I taught a class on cryptography, mathematics, to honor students.
Okay.
And the first few times I taught it, I didn't use this because like I learned about it from working with Amy, and then later times I actually implemented the stuff I worked with Amy on elliptic curve cryptography into later versions of the course. And then for Brenda, yeah, I had her in class as well. So a lot of times the students take a class with me and then they are an honor student and they need to work on a thesis. So then they ask me
Okay.
if I have an idea for a project.
That's a natural way for things to happen, actually, isn't it? Yeah, yeah. Any other, Ann?
Yeah, I love this. I mean, I don't really know anything about cryptography, but there are a couple of things I just wanted to share. We have so much fun working with students on projects at a whole variety of levels. But one of the things that we do is in our physics department, where students who are taking physics for pre-med of all things, or other biology and science courses, we require them to come up with a project of their own, usually in twos. And some of the projects are ones that would be great initiators of the kinds of things that you're talking about. Heat flow is a huge one. We do a heat flow model, for example, in my physiology course, and then the students will go and do a heat flow model in their physics course. And it would be a great jumping off place for projects. It's the Olympics this afternoon, along with the Super Bowl. How do you spin on your ice skates? Another fantastic possible mathematical model. And I found that having students work in pairs often allows maybe even two different projects, but a lot of synergy in getting these projects to go. So I'll just share that, particularly if they're across borders. And in your case, you have at least two that were physics to math. So it struck me as, a possibility of pairs might be very fun.
Yeah, the idea of pairs is a lot like having regular office hours. You have some person for accountability, and in Mike's case, you have some common time for accountability. Like, I got to meet him on Thursday. I better have something to say. And when you're working with a partner, you don't want to let them down. So those are all good accountability instruments. Okay.
Yeah.
Any other comments, Mike, before we close out? This is the last talk of the last day, and maybe between what Ann and Becky offered us, albeit to a limited audience, we saved the best till the last, I guess, in a sense. Mm-hmm. But I really commend all three of you for doing what you're doing with students and trying to get them involved in bigger thinking. And as a person who has a pure math background and finally, came to the road to Damascus and the conversion to applied math, I could see where I would have made a change much earlier if I had one of you three. because it would have shown me that there's all kinds of fascinating things you can learn with this mathematics and because of it and in support of it. So I want to thank you all again for participating. I wish you well, and I'm going to, unless you have another parting, I'm going to close this session and go to another room to give a formal closing. And thank you again, all three of you, and be safe. Okay.
Thank you.
Bye-bye.
Thank you.
Thank you, Brian.
Bye.
Bye.